I will remove this thing. Can I? No, it's the schemes. You know, Microsoft cannot guarantee that our data would be safe. So maybe we should switch to something else.
Absolutely.
And
What? How to replace?
I minimize and also share your screen before.
So should I disconnect once again?
No, just share your screen. You don't have to disconnect.
What about show only active speaker?
No, it's
And
okay. And
this is okay.
We're recording?
yeah, okay.
We are recording.
Where it so it was not so long ago this game.
Nice.
So should we wait a bit for the people online or like 1 minute? Let's wait.
Actually, only Wang accepted and is not here, so maybe.
It has some package, so
1 minute.
it's a minute left, so
Okay,
it's
let's
we
go.
can anyway start. Say,
Oh, there is Esther. Yeah, there is Esther. So can you just put on your camera so she can see us?
okay, let's try.
1 more minute. Yes.
Perfect. And then you can go back on the door. Nice. Thank you.
Nice, okay. Yeah, today, no, let's solve this minimize. Yeah, perfect. It took us some time, as every time it seems, but we managed. With every Teams recording, it's faster and faster. Okay, so yeah, today I will talk about two things, which both inherently geometric, but for whatever reason, they're still kind of except of me that is representative of both communities, they're still not kind of tightly connected and coupled. And one of them is message passing, like which I hope everyone here is a member of. And the message passing talking inherently about the structure of your generative model, about structure of your graph, how your nodes connected, what edges are shared. And it's if you're still not a member of a message passing community, the picture for that is on the right. And there is information geometry, and information geometry mostly talking not about your model, not about your generative model, and not about geometry of your generative model, but about geometry of your variational family in variational inference, if you know what is it. But basically, you can represent your generative model in some form of a distribution. It could be like very generic, it could be like normal, or it could be like normalizing flow. And information geometry studies how to make inference on these specific form constraint models fast or stable or accurate, but it studies this field of inference. And first, let's guess a bit on what you subscribed. Maybe I'm following this Ben DeVries for like the last 3 years. And from his talk from 4 years ago, he kind of talked about like hype cycle and natural inspired AI, and what does he mean about what is natural inspired AI, and what you subscribe when you kind of somewhat join into this lab. So, and more or less in the very degree exposition, natural AI is something that he doing it also like very consistently through the year to the year. He just repeating this agenda. It's just becoming better and better. But the idea is that, like in classical physics, we can recover classical physics law from some form of a principle of least action. The same thing we could do for intelligent system, and he called this Bayesian mechanics. And it's kind of attributed for Carl Princeton. However, Elbow is like known long ago, but I think to what is actually true, the first one who recognized that it's actually some form of the principle of exception, I think we can attribute it to Carl Princeton, so here we all could agree. But it's kind of, so inevitably, if you want to do natural intelligence, you would study this functional in the middle. You will study this integral of QS, QSP, SDS, and you will try to find it minimum. So if you subscribe to natural intelligence in the form of Bayesian mechanics, this is the thing that what you should do. And before we will jump to the main topic, I would make a small interlude. So recently we talked with Alex, and she told me about Buddhism, and it was like, well, Mykola, pain is inevitable. And what I mean by pain is inevitable, and that if you solve in some form of I will start. I think everyone kind of know what is the least square regression problem, and everyone knows. We can easily derive it on a board right now. So you just take derivative with respect, you take your gradient with respect to beta, and you will obtain this nice expression for the beta start, like optimal stationary point of least square regression on the right. That is the problem. So if your number of your features, like x's here, this matrix that we represent would grow would grow in the sense you will have a very big beta, or it would be very hard to invert this xp in the middle. So the main problem of how like when people started to study linear regression was how actually to invert it. This was like quite a hassle in 19th century. I understand that that's quite a problem of long ago, but we quite improve hours of time, and the real thing but suffering can be avoided. It's also what I learned from Alex. And the idea that probably you should not consider closed form rules so straightforward, like, oh, I derived some closed form rule, then I need to just naively execute it. And what people in linear algebra community figure out, and I would not dive into it, but let's take it like some form of interludes, which will come to Bayesian learning group, that, well, if you will form some form of you can rewrite this problem as the solution of some linear of a linear system. And first thing, it can be made through the gradient descent. It actually can converge very fast. It's also numerically stable. So most of the time, when people right now, they're trying to solve linear regression, they do not try to invert this matrix on the left right now. It acts like this gram matrix, it's also called. And this is kind of lesson to learn, I think, for all that doing some form of any form of engineering. Straightforwardly to solve something probably is not the best solution. So we cannot avoid. So what does mean pain cannot be avoided? That any solution for the problem on the left will, how you will come up with it, will satisfy this equation. So anywhere, somehow your algorithm will multiply this matrix inverse on some form of a vector. The question only how to do it efficiently, but you cannot avoid this multiplication. And well, thanks for this, that you stayed with me with a small interlude and you learned how to do linear regression. We return to our problems that Baird degrees specify as a form of Bayesian mechanics. And it's like in the classical variational inference, what we're doing, not message passing, but well, we have some form of generative models. It's rolled here is P, and we have some form of variational family. And here on this graph, what I'm showing, I have a mixture model, where I want to fit in this mixture model some form of a Gaussian. And I can select different form of a Gaussians. I can select diagonal Gaussians, or can select full covariance Gaussians. But at the end, what we want to find out, we're saying that the best possible posterior of this Bayesian mechanics result would be something that solves this at minimum. And no problem with that. I will talk about. I need some setup. However, the result that I'm talking here would be generic. I like to make it a bit more specific and a bit easier to follow. It's mostly about it will be presented on the basis of exponential family. So what is exponential family? Everyone knows what is exponential family, or if someone does not know, then just a lot of distributions. Like normal, beta distribution, or log normal distribution, like a set of exponential family distributions actually unlimited. It's more or less the distribution that follow this form on the up. That's Q lambda. That if you have some exponential family distribution over theta, it means that it's simplified, but because I don't have like some basic functions here, but well, it's more or less following the form above. And let's imagine we want to solve variational inference problem on this set of some subset of these exponential families. So like normal would follow it with t theta equal to x and x transpose x. So you can select this by selecting this t theta. You can select different exponential families. And well, what does it mean? Right now, we specified some form of parameter, and we can respecify this like non-parametric problem arg minimum over q in this mass in this big Q as a stationary condition over some form of the like finite dimensional parameter. And yeah, we just taken the derivative. I just did nothing. So I just literally rewrote the line in the middle, just put a gradient to the left of this expression and just wrote 0 because it's like literally stationary condition for this exponential family. And well, what is interesting with exponential families and why do we like it? Because for exponential families, and why I present this result on it, but it can be generalized, but it's just but derivation is just not so pleasant. You can actually show that that the gradient with respect of this thing that we called entropy minus entropy or minus entropy, the most important decide what is the gradient of the entropy, is actually pretty straightforwardly can be derived as from, because yeah, basically what is the first equation? In the first equation I have something log linear and the exponent. With logarithm I just remove this exponent and I obtain like this expectation, and I'm using like very straightforward facts about exponential family theory. I can arrive to the fact that it's actually equal to the Hessian of the log partition multiplied by lambda. And so what is it? So what is it? Maybe why it's so important? Because well, it's some form of exposition. This Hessian of a log partition for exponential family, once again, just take the log, take the gradient, you will obtain this exact result. That is like it's one step, almost like one step derivation, or like 3-step derivation. You will see that the thing that for whatever in classical statistics called Fisher information is actually Hessian of the log partition for this specific parameterization of these families. And why it's so important? Because, well, if we will specify the stationary solution in terms of this natural parameter, it actually can be specified as a solution of this nonlinear equation with Fisher information, this last equation at the bottom, can in this form. And what does it mean for us? It means that if we solve a variational inference problem, like in linear regression, or we know that our beta coefficient would follow the equation of the like inverted gram matrix, any solution of variational inference, however how you come up to it, if it's a stationary point, it would follow this natural gradient. So anyway, whatever you do with your variational inference, and however the derivation here was made for exponential family, it actually can be generalized even for non-parametric model. The result of the variational inference would follow the stationary condition. So there is two, and right now you can take two roads. Just admit that you don't care that it follows a stationary condition, or actually use this new information that we just obtained. And how it can be used. I like this very example that I first wrote in Cambridge. Yeah.
Do you want questions now? Or?
Yeah. We can have some series of questions right now. Just but let me check the time that I don't take in too much time. Maybe I'm taking it. Oh, it's like 12 minutes.
No, it's okay.
Yeah, it's okay. So yeah, we can take some round of questions.
So you have L star is f of L star. Or lambda star is.
Yeah, if lambda star is a stationary, it would satisfy the stationary condition of the variation of the KL, it would mean that lambda star would be solution of this equation. So you have lambda star is kind of like x, right?
Yeah.
And you have some function of x on the, sorry, I did not understand.
So the right-hand side seems
Yeah.
to be the stationary condition, so the right-hand side has to be 0, and then the left-hand side is the argument that imposes the stationary condition. Are you not mixing the two?
No, we can, maybe I did it just a bit fast.
Maybe you can do.
Yeah, we can, no, I mean, I think we can, I think it's important question, I can answer it. Look on the,
0, right?
look on this equation, a second equation, look at this
Lambda
equation.
0 is the minimizer.
Yeah.
To the parameters for which the stationary condition is satisfied, then f lambda star and the gradient of lambda evaluated at lambda is lambda star should be 0. So the right.
This is right. This is the expression which we told.
Yeah.
We know that this would be Fisher information multiplied by lambda.
Yeah.
We know this, so we can move Fisher information multiplied by lambda to the right, right? We can multiply it by the Fisher lambda. We can invert by Fisher lambda.
Yeah.
And we will obtain the expression here.
There's no plus at the bottom. It's just this second in the second line. It's just this equation rearranged.
Yeah, I took this equation and rearranged it, and said that if lambda is maybe what I should do is.
Hold on. Okay, so you go back to the linear regression. Right. So here you have on the bottom row you have beta star.
Yeah,
beta star.
Yeah, but it's a linear program. Here the beta star can be written without beta star itself.
Yeah. On
So
the right-hand side. The
right-hand side does not depend on the beta star, right?
Yeah. But then, so you define beta with the star as the minimizer.
Yeah.
And in this case, the right-hand side is the solution of the first line.
Yes.
And then if you go back to the variational posterior one here. So hold on, so one slide back. So f of lambda is, no, forward one. F of lambda, the Fisher information matrix. So lambda is an argument. So you put a parameter in, and then you get a Fisher information matrix out.
Yes.
And forward one. Now it looks like the left-hand side, lambda star, defines the optimizer, defines the lambda for which the stationary condition, for which the gradient is 0.
Yeah.
And now on the right-hand side, you evaluate the gradient at
lambda. Yes.
At
On the
lambda
right-hand side, evaluated in the lambda star.
So the right-hand side should be 0. If you define lambda star,
No,
the
it's
right-hand
not
side should be 0.
No, it's not 0 because why anything on the right-hand side should
You
be
can just move lambda and start
It
to
should
the
be.
right hand side and then push that. to
Look
zero.
under this equation.
Find a lambda star for
Yeah.
which they did this equality.
Let's talk about it after that.
No, it does not need to be 0, right? Okay.
This is
This is a stationary.
not lambda star or not?
This is not a definition, it's a solution. If lambda star is a stationary point, it would follow this equation.
I think I might understand the confusion. So the gradient of the expression expectation of q of minus log p plus h of q should be 0. But
This is only true.
so so
This is only
this is
true.
only the gradient of the log of p and not the gradient of h of q.
So the gradient.
the custodial
is
gradient-
in the Fisher information. That's
Yeah.
written on the right.
Yeah.
Does that explain it? or not?
You should find the lambda star. for
Yeah,
this equation.
I think I can
then you have
derive it step by step after the meeting to the router on the board. Oh, we can do that right now, by the way. No one stops it. But yeah, well, okay.
I thought it was a small question, so.
Yeah, it's a small question. We can derive it in like 1 second, but it's like what expression in the lower, like it's a one step from the second equation to the left side. Second equation to the left side, if you open it and rearrange, you will move the second term to the right. You will obtain the expression down.
Yeah, but my confusion is before you identified, you had beta as a parameter, and then you said beta star is defined to be the right-hand side. So the right-hand side is a solution.
Yes.
And now you have an equation on your slide that says lambda star.
Yes, stationary condition is non-linear. So on the left and on the right, it depends on lambda. So
Yeah, but then I would write it as lambda
Yeah.
is f of lambda right? Because you still have to iterate until you find the optimal.
No, it's at the stationary point, lambda star is actually equal to it. It's what iteration scheme does, right? So if you have a gradient scheme which you repeat, actually at the stationary point, you will have a quality on the right and on the left.
But if you evaluate the gradient,
If a lambda star is stationary condition, if I will put it on the right, I will obtain lambda back.
but if you have a function that you are minimizing with respect to an argument,
I'm not minimizing
you
actually, it's a
evaluate
stationary
gradients
condition.
for the
Stationary condition.
But I think that it's like next body explanation could be easier, so maybe we wait for
Yeah.
10.
Yeah, and I will
But that's then later.
Yeah. I liked, this small interlude, not so small, I'm sorry. But I really like this example which I first learned in the Murphy books, and it turned out not Murphy come up with it. So I found actual guys who did it first. They come up with a so we know right now, we all agree that the stationary condition of variational even depends on Fisher information. So it means like unavoidably we can either not use it and be suboptimal, or either we need to find out how to use it. And I like this example because here Fisher information is actually very, very smooth and almost not changing through their parameters phi. So it's the picture why knowing the Fisher and not knowing this is better would be very, very useful. But it's like very coupled normal distribution where you could not move your mean on the one component freely from the other component. And variances are also dependent. It's like a form of Gaussians where not only they have not only shared mean, but also very, very coupled means. And I like this. I like this specific normal family because on it, because of sufficient information, somewhat global. You can rearrange you can just multiply by minus Fisher inverse your parameters and build two gradient fields to the optimal point, and you can see that how gradient fields converge to the optima with a Fisher metric and how they are not converged, they very steep, they have this correct one mean convergence, but another one is always overpowered by another. So you actually need to renormalize. And returning to, it's almost mathematical slide. So we did some form of the very of this exposition, but actually, like this two station, it's almost like they're almost the same. It's like just the same thing. And if you will, this is a new result which I find out yesterday in the reading in new paper of Khan, that actually if you doing a lot of assumptions, so basically we know that we need to compute Fisher, and the question is, can we compute Fisher efficiently? I will not spend time on this presentation like explaining in the deep that is it possible to compute Fisher efficiently or not. It's just believing that it's possible, and we can, but the mathematics is a bit coupled. But the actual result right now that we can build very, with the actual result in information geometry right now, that we can build very, very big diagonal Gaussians with a speed of convergence comparable to deterministic algorithms. The only problem right now is that we kind of somewhat lost the baby when we drop the water, that actually if you will look on the performance of this big, huge family of diagonal Gaussians on the big models, they actually perform most of the time not better than deterministic algorithms. And that is first somewhat disappointing. And however, computational complexity of deterministic algorithm and the Bayesian algorithm is actually the same. So for me, it's like kind of somewhat, it's right now like somewhat an open question, how to scale this Bayesian models right now to the very big sizes without not assuming too much of a mean field and actually to obtain some performance. That if you will assume very, very big Bayesian model and you will actually assume mean field everywhere, performance of this model will be actually worse than deterministic solution. That is somewhat the problem of for us in Bayesian field right now to solve. So how tightly couple two structures. So information geometry right now shows us that, well, you can't have Bayesian algorithms that runs on the speed of deterministic ones. The question is, can we have the speed of deterministic algorithms and also have better performance? And unavoidably, I see only solution for that, and it's called message passing. And message passing as a field tightly coupled to beta free energy. It's the thing that's written up, right? Like, and all message passing algorithms coming out of this, out of the beta free energy. And this is a new result. Don't tell anyone. I haven't published it yet. But actually, for the same result that Khan obtains for non-decoupled models, you can obtain the same stationary condition for the message passing, assuming exponential families or some parametric families. I haven't scaled it back to non-parametric, some forms of the same stationary condition. Well, but in difference with the Khan's approach, where he has here huge integral over whole model, I need to take integral only of the subparts where this h actually is used. And I'm sorry, I wanted to draw a factor graph for this model, but it's so big and so coupled that it was somewhat broken, but you should imagine a form of the huge lattice, where for each point in your lattice, you have a nonlinear observation. And the goal is like from these nonlinear observations to infer back your latent state. And it basically implements exactly this stationary condition. And on this toy model, basically we have some form of a smooth field of a temperature, and we want to infer backwards our latent state from the noise model. And first we can do it. The question is always in the balance, because what we kind of see like connection force between latent fields and like some form of a prior. And I think it's part coming in messages completely from message pass. And what we see here, like this connection force higher, lower, is how one geometry fights another. So we have like nonlinear geometry coming from our observation, which depends on connection force between your latent fields. Yeah, go ahead.
You should explain a bit more what's going on, I think, with what connection force is.
Yeah, yes.
What's the left image? And if you go to your plot, what's the left image? What's the middle image? And what are we seeing on the right?
Yeah, what is the left image? The most left image is unknown true state. The middle image is a noise observation or noise observation with a missing data. So if you see a yellow point in the lower picture, it means that if yellow pixel is mixed, it means that it's not observed. And what we see on the right is the result of the inference.
So it's a masked, noisy observation of an MNIST image.
Yes.
Which we're trying to reconstruct.
Yes.
Given an Ising model.
Yes. Given the structure.
Yeah.
So, and however, yeah. So what is important is that I tried to run this experiment because we have this generative model, right? And it's actually also a generative model which you can just evaluate. You can put there some parameters for your mean, some parameters for your variances, and you can recover and just run on I1, this algorithm that this Shen proposed in the ICLR. You can run this on this very model. On this very model, you can run this full diagonal Gaussian problem without any message passing. The problem, it does not converge. So for me, it seems I will not be like too overconfident right now that the actual structure that missed completely right now in information geometry field from the model is actually very important for like this, something like low pass filters on the near the observation. And that's, I think, yeah, I'm done by the way. So any questions?
I did not understood what brings this the factorization, the fact that you're using message passing and factorization compared to Kahn's method that is just minimizing.
Yeah, the difference is in the stationary condition, right? Because in Kahn's method, what you will have here the expectation of Q over whole log P here, that is this model upright, that is model up. So you will have your marginalized normals. You take the integral of the whole model over it, and you do in a step. That's what Kahn algorithm prescribes. What we prescribe is different. You computing only local expectation over your marginals where actual H is used. So that is the difference.
But why it's bringing something plus? Because you said the Kahn missing some kind of.
Yeah, what is it? Yeah, that is a good thing because the problem is, I think I'm not so overconfident right now to say, but I think the actual issue is when you take an expectation through very, very big latent states, like here is like 784 latent state. If you will naively try to take expectation of the sample of the mean field without, they will be overspread. So actual samples on each marginals, they will not depend on each other. And the estimator in the Kahn's estimator will be very, very noisy.
Mm. So the issue is not the formula, but the fact that you have a.
I think the issue is the formula. And I think that it's noisy, not because it's not noisy because it's like because of the formula, it's noisy. It's not noisy by itself. But because it's an expectation of such big latent state of some big model, its gradients is actually noisy. Yeah.
I think it's related to Wouter's question, but you prescribe a stationarity condition for lambda star, but I assume you need the actual lambda, you need the stationary point, right? How do you get the stationary point? Because this is just a condition.
Yeah, it's a condition. I'm not talking how to get to it, right?
Yeah. So that's a question.
Yeah.
How do I get lambda star?
Yeah. How to get to the lambda star? That is about. You think it's about the question?
I think it's where Wouter got his confusion because I think Wouter interprets this stationarity condition as a way to obtain lambda star.
Yeah, but yes, but it's
not. It's a stationarity condition. So my follow-up question is then how do I get lambda star?
Yeah, in the Kahn algorithm, we have two algorithms with stationary conditions. And here, how you can implement it very naive. You initialize some lambda, you put it on the right, you obtain new lambda, you put it here again until convergence.
Right. Yeah. This would converge. So
this converge. Yes.
Okay.
Yeah, that's the point. Yeah, it's like a mean field message passing scheme. You know that at the stationary condition, your marginal should be equal to multiplication of your mean field messages, right?
Right.
But with every iteration, it's convergent to it.
So my confusion would be that if you say that you have a superscript, right, with parentheses, and then in the parentheses some iteration. So you start with lambda superscript 1 is minus f lambda superscript 0 gradient.
Yeah, so it will be stationary scheme. So from stationary condition, we can generate a stationary scheme, right?
And my confusion was usually if you use this asterisk symbol, then that is the station, that is the solution.
Yeah, but in the solution, equality would hold, right?
Yes, yeah.
So there is no problem in this
Well,
equality,
that was my confusion. Is it a definition or is it you mix up?
No, it's not the definition because
If it was a definition, then you mix up the stationary condition with the solution. Right? But if it's just an iteration, it all works out.
Yes. I mean,
I can write this out if we have a.
Yeah, we have some time, I think, right?
Yeah, but
I think it's very clear at this point.
It's 38 minutes. You said me that we have like half an hour.
Yeah, just bringing some markers, continue the.
Okay. But here the stationary condition, you compute marginal. It's in the complete mean field stationary condition. You compute your marginal. You run mean field. You compute mean field messages. Over these mean field messages, you recompute your your lambda parameter back.
Yeah.
Okay.
So I was going to say, you asked whether it's about the question, but if you ask, it is also about the question.
Yeah, that's true.
Yeah, but I meant another one.
It was related to
Yeah.
to your question.
But so, okay, so if I understand this correctly, your sweeping connection strength
Yeah.
is animation.
Yeah.
And so if you have observed all the pixels, then, all right, so for some values of the connection force, you do not unnoise it, right? So the noise is dominant.
Yeah.
For some values of the
Not noise, a prior mode. If your connection force is very, very high, it means that your latent generative model is very strong. It's why we see just a flat field. But if your connection force is very, very small, there is almost no connection and your observation noise dominates. So first we see there is no recovery, connection force is yet too small. And then
this is a bit like sort of a common game thing.
Yeah, it's exactly like a syncretic Kalman game.
And then if you have missing observations, there's just not enough. But if you rely on the likelihood screws up your result. It doesn't
That's if your connection force is very small, you trust your likelihood too much.
Yeah. Okay.
And then, okay, so the final question is, so you made this suggestion that there's a tension between the force of the geometry and the force of the...
Yeah. With the message passing geometry, the geometry of the model, and the geometry of your variational family. So it's kind of what connection force represents, right?
When you say the variational family, do you mean field? Choose a certain factor?
By variational family, I mean form constraint on the edge. I mean here it's a normal.
Right.
So the point is that you granted all these derivations to the variational influence with exponential family, and that gives you this information geometry, and then you would say, but then if you additionally add the constraint, the factorization constraints of message that lead to message passing, then you actually get the computational advantage.
Not computational advantage because, well,
Over Kant's method.
it's not a computational advantage over Kant's method. Kant's method, not the Kant's method, but Shen Yu. And Shen's method is already as computationally expensive as deterministic method. So if you will take basically Shen's method is something like the following, it's a bit with tricks, but it's almost like that. You take your variational family to be independent Gaussians with separate variances, and you do tricks about computation of your natural gradient. And this approach is already as computationally expensive as deterministic algorithms. The only problem right now is not how to scale it. It's so if we allow deterministic algorithms like this to exist, then we should allow Bayesian approaches like this to exist. So there is not the main question. The main question and the main problem of the Shen's method that the quality of it is actually worse than the quality of deterministic algorithms. That is the main issue to overcome. And the question is how to stay the speed of the Shen's algorithm, however, remain or overpower deterministic algorithms. So from the computational perspective, it's already scaled. The question is, can we, with message passing, actually obtain more stable posteriors to actually have a better results?
And you get all the benefits of the probabilistic approach, like dealing with non-observed.
Yes. Because, well, if you're dealing with some form of deterministic algorithm and give you always better predictions, well, it's very hard to advocate for Bayesian approach. But if Bayesian approach would not only work as fast as deterministic algorithm, but also would give at least better prediction, or at least at the same quality prediction, that would be beneficial, right?
Yeah, aside from the fact that the Bayesian method gives you Bayesian evidence, and so the metric to compare to another one.
Yes, that's also true, but when we do in variational mean field, your evidence is not really comparable between the two different algorithms. You can compare only inside one family, right? So, I mean, once you do in variational inference, it's already becomes a bit philosophical, but there is a paper, I will not recall, but basically they compared evidence for different models. And the problem was something like, well, evidence once inside one model, you can treat it as a fit of some fit of convergence. But once you have two different models, evidence in higher or lower in another one actually doesn't tell you anything about your actual evidence because it's like it's an L, right? So it's a bound.
Right, so this is the paper that Albert also talked about, so.
You can correct for that.
You can correct.
Uh,
Stupid question.
no, go ahead. The
So,
best question.
information geometry, here you have a natural gradient instead of.
Yeah, where is the natural geometry in this method is a stationary condition that depends on Fisher information. This is part of informational geometry and this part of message passing.
Right, but so the difference in accuracy, the difference in performance between the two models must now rely on how close they are to the true parameter. It's because you're essentially comparing two different optimizers and then claiming that one is more
But
accurate
yes,
than the other.
yes,
So then what you're saying is that this optimizer gets you closer to the
yes,
true optimum than the other.
yes,
And because it gets closer, it gives better performance.
yes. So it's not a stupid question at all. Okay.
Super.
And